Today we are going to be talking about instantaneous and average power in AC circuits. And this is the first of 3 lectures having to do with power in AC circuits, which is for this class. So what we are going to see, starting today really, is that we're going to be inundated with equations, but I'm going to make a point to kind of show you which ones are the most important, meaning that you'll get the most use out of, and then we will pare those equations down for specific circumstances. So it's not important that you remember the ones that are useful for specific circumstances, but in the long run, if you can use them, excuse me, it might save you a little bit of time. Not a ton by any stretch of the imagination, though. Okay. All right, so let's say that we have a network, and it is a simple 2-terminal black box network like we've utilized numerous times in this class. And we excite said network with some sort of sinusoidal excitation function such that the voltage drop across the terminals of the network is V of t, and the current flowing into the network is I of t. And because we are sinusoidally exciting this network, our expectation is that V of t will be of the form Vm cosine omega t plus some phase angle theta v, and I of t will be Im cosine omega t plus some phase angle theta I. It should be, hopefully, extremely unsurprising that the instantaneous power absorbed by this network is simply going to be the product of our voltage and our current, because that's all power ever is in an electrical system. Okay? So I'm going to expand this out. So we'll have Vm cosine omega t plus theta v multiplied by Im cosine omega t plus some phase angle theta I, like so. And luckily for us, we have a trig identity that allows us to take into account the product of 2 cosine functions. Okay, so that trig identity, which I'm going to do over here in blue, is cosine, let's call it alpha, times cosine beta is 1/2 cosine alpha minus beta plus 1/2 cosine alpha plus beta. Okay. Where in this case, alpha is this whole angle omega t plus theta v, and beta is this whole angle omega t plus theta I. So when we apply our trig identity, we're going to have 1/2, and then our magnitudes are going to multiply by each other. So this is going to be Vm times Im, and then we're going to have cosine of alpha minus beta. So that's omega t plus theta v minus omega t minus theta I. The omega t's go away, and we're just left with a term theta v minus theta I. And now we're going to have the second half of that trig identity. So once again, we're going to have 1/2. Our magnitudes multiply together. And now we're going to add those angles. So that's going to wind up giving us, cosine twice omega t plus theta v plus theta I.
So sorry, is that a 2 omega t?
That is correct. Twice
Okay.
omega.
Thank you.
So I'm going to put a box around this guy right here. Okay. This is one of those important equations where if you remember practically any relationship from today's lecture, please let it be this one. Let me explain why. This particular instantaneous power relationship is applicable for literally any two-terminal electrical network. So that means it could be a resistor, a capacitor, an inductor, or any combination thereof, a voltage source, a current source, etc. This one will work for literally everything. The ones that we are going to derive from this will only be able to be used in specific instances. Okay, so this is the mother sauce, if you will, for this series of equations. So if we look at this thing, we can recognize that it has two parts, okay? So the first part, the 1/2 Vm Im cosine theta v minus theta I, well, 1/2 is a constant. The magnitude of a sinusoidal voltage is a constant. The magnitude of a sinusoidal current is a constant. The phase angle of a sinusoidal voltage is a constant, and the phase angle of a sinusoidal current is a constant. So this whole first term is literally just a constant. So this represents a DC contribution to our instantaneous power. Okay. Then over here, we have an AC contribution, or a time varying contribution to our instantaneous power, where this AC contribution is oscillating at twice the frequency as our voltage or current. Okay. So if I were to plot the instantaneous power absorbed by our generic network, it might look something like this. Right. So this is going to be P of t. This is going to be t. And this dashed green line right here represents the DC portion. And then on top of that, I'm going to superimpose an AC portion. If my stylus will agree with me and write. So something like this, right? Where, once again, this is our DC power part. And then the maximum value, and we have the AC value sinusoidally oscillating around this DC value. Okay. So a couple of quick things here, right? For this particular instance, sometimes the instantaneous power absorbed by our network is negative. What does that mean?
I mean, it's drawing power.
So if it were positive, it would be drawing power because that's what absorbing power means. So instead, if it's negative, that actually means that for specific instants in time, our network is supplying power. So anytime that we have any sort of energy storage elements in our circuit, be it a capacitor or an inductor or both, we will see that our instantaneous power behaves this way. So our energy storage elements allow our overall network to sometimes act as the source, and the excitation signal sometimes is acting as a load. We're going to investigate this concept a little bit more in tomorrow's class meeting, specifically when we talk about the power factor of a steady state sinusoidal system, okay? But the fact that we have negative values here means that our generic network is capable of storing energy, and then it releases that energy back towards the source. Okay? Another thing that I want us to observe from this is what's going on with the DC power, right? So exactly half of the time, the instantaneous power is above this DC level, and exactly half of the time, the instantaneous power is below this DC level. And we can see mathematically that the AC power is symmetrical about that DC offset. So this means that this DC offset is a representation of the average power absorbed by our system, okay? So we can call this, my stylus will write, capital P average, where I'm using a capital letter to acknowledge that this is a DC quantity, okay? So the DC portion of the instantaneous power is therefore the average power absorbed by our system. So now let's use these relationships to determine the instantaneous and average powers absorbed by resistors, capacitors, and inductors specifically, all right? So a couple of things that I want to remind you of. For a resistor, we found that the magnitude of our voltage, Vm, was equal to the magnitude of our current times the resistor value, and we found that the phase angle of our voltage was equal to the phase angle of our current. This was during our one of our first lectures on analyzing this steady state sinusoidal circuits in the frequency domain. We came up with these relationships. Okay. So what we're going to do is we're going to make substitutions using these relationships to express the power absorbed by our resistor only in terms of voltage related quantities and only in terms of current related quantities, because our original expression requires us to know what both the voltage and current are doing, okay? So let's work with voltage relationships first, okay? So we could say that PR of T is going to be equal to 1/2. Vm is going to stay the same. Im is equal to Vm divided by R. So if I multiply Vm times Vm over R, I get Vm squared divided by R. Now I'm going to have cosine theta V minus theta I. Well, if theta V and theta I are equal, then what is the cosine of 0?
1.
1, absolutely right. So we're going to have 1, then we have a 1/2 Vm Im, so that's the same thing as 1/2 Vm squared over R. Now I'm going to have cosine twice omega t, and since theta V and theta I are equal, I can call theta V plus theta I twice theta V. So now we have expressed the instantaneous power absorbed by a resistor purely in terms of voltage related quantities, right? We only need to know the magnitude of the voltage and the phase angle of the voltage in order to solve for the power. What would the average power be?
1/2 VM squared over R.
Exactly right. Just the DC part of this instantaneous power.
Okay, can you explain that? Or is there nothing to explain there? Is it just, I don't know.
Well, I explained it by looking at this graph, right? So we have a DC portion and an AC portion. The DC portion of the instantaneous power is always the average power because it is the average value about which the AC portion oscillates.
Okay, I gotcha. I see, thank you.
In terms of current quantities, we could say that PR of T is equal to 1/2. So now we're going to express VM as IM times R, multiply that by IM, gives us IM squared R. Cosine of 0 is still 1, plus cosine twice omega T plus twice theta I. And again, our average power will now just be the DC portion of this relationship. So 1/2 IM squared times R. So one thing that we can hopefully observe really quickly here is that these average power relationships are very similar to what we saw in DC circuits, right? So in a DC circuit, we could express the average power absorbed by a resistor as V squared over R or I squared times R. Well, here, since we're dealing with sinusoids, it's the same relationship. We just have to multiply by a factor of 1/2, and it's because of the trig identity that we use when we multiply sinusoids together. Okay. So almost exactly the same relationship, just scaled by a factor of 1/2. All right. So now let's look at an inductor. So in an inductor, VM was equal to omega L times IM and theta V was equal to theta I plus 90 degrees. Okay. Again, these relationships come from our first lecture on setting up the rules for analyzing circuits in the frequency domain. So we're going to do much like we did for resistors. We're simply going to make simple substitutions to our generic equation to see what shakes out here, right? So we're going to have 1/2. VM is going to stay the same. IM could be expressed as VM over omega L. So that means we're going to have VM squared divided by omega L. Now we're going to have the cosine theta V minus theta I part, right? So if theta V is equal to theta I plus 90 degrees, then theta V minus theta I is theta I plus 90 minus theta I. What is the cosine of positive 90 degrees?
-1.
I disagree.
0?
Sorry.
Zero. Cosine of 90 degrees is 0. Okay. So what does that mean that our average power is?
0.
0, right? Because this first term is going to be multiplied by a factor of 0, which means the average power absorbed by an inductor is 0. So we're only going to have an AC portion. So this is going to look like twice omega T plus twice theta V minus 90 degrees. In terms of current, we're going to have 1/2 Im squared omega L cosine twice omega t plus twice theta I plus 90 degrees.
Shouldn't that on the top one be 2 theta V plus 90?
No, so if, let me, so theta V is equal to theta I plus 90 degrees, right? Which means that theta I is equal to theta V minus 90 degrees. So when I add this plus another theta V, it comes out to twice theta V minus 90.
Got it, thank you.
For a capacitor, we have the relationships Im is equal to omega C times Vm, and we have theta I is equal to theta V plus 90 degrees. So this is going to give us PC of T is equal to 1/2 Vm squared times omega C. And then we're going to have the cosine of negative 90 degrees when we do the cosine theta V minus theta I. What's the cosine of negative 90?
0.
Exactly right, which means our average power is what?
0.
Exactly right. So for either of our energy storage elements, the average power is 0. Okay. Now we're going to have cosine, excuse me, twice omega t plus twice theta v plus 90 degrees. And in terms of current, sorry, I need to put that in the numerator because I'm going to be dividing by omega c. That's twice theta I minus 90. There we go. All right, so these are our relationships for resistors, inductors, and capacitors, where we only need to know the voltage drop across the element or the current flowing through the element. If we have any combination of elements or voltage or current sources, we have to use the relationship that I've boxed up here in red. Okay. All right, so I am trying to decide on whether or not I want to work an example problem now or more formally derive the average power relationship that we gleaned from our graph, because it's going to help us understand a couple of things later on. So I think I'll do that first. Okay. So this is kind of a subtopic here. Average values of periodic functions. So we are going to more formally come up with a relationship for the average power. And it will wind up matching what we were able to observe. And then we're going to wind up using this relationship quite a bit when we talk about complex power relationships in our next class. Okay. So if x of t is a periodic function, meaning that it repeats itself at regular intervals. Then the average value of x of t is given by x average is equal to the integral over exactly one period. I'm going to choose to represent this as from 0 to capital T, but these don't have to be our bounds of our integration. It literally just, we need to integrate over exactly one period of x of t dt. And then we divide this integral by the time interval of the period. Okay, so we integrate the function over one period, and then we divide by the length of that period to get the average value. For our instantaneous power, this looks like the integral over one period of, it's going to be 1 over t times the integral over one period of p of t, right? Well, we have an expression for p of t. That is 1/2 Vm Im cosine omega t, excuse me, that's not right. Cosine theta v minus theta I plus 1/2 Vm Im cosine twice omega t plus theta v plus theta I, close my brackets, dt. What I'm going to do now is I'm going to break this expression up into effectively two integrals. So we're going to have 1 over t times the integral from 0 to t of 1/2 Vm Im cosine theta v minus theta I plus the integral from 0 to t 1/2 Vm Im cosine twice omega t plus theta v plus theta I dt. Close second. So I want us to look at that second portion first, okay? So that portion of the instantaneous power is a pure sinusoid. So if I attempted to plot it, it might look something like this. If I were to integrate that signal over one period, what would I get?
Zero, right?
Exactly right. So this positive area would be canceled out by this negative area. So we would get 0. Okay. Anytime I integrate a sinusoidal function over an integer number of periods, I will always get 0. So that means this whole term is simply 0. So now let's look at the other thing. Well, as I pointed out earlier, literally all of this bit right here is just a constant. So I could take it outside. So that means that I would have 1 over t times 1/2 Vm Im cosine, excuse me, theta v minus theta I times the integral from 0 to t of dt. Well, what's that integral from 0 to t of dt doing? It's just canceling out this 1 over t in the front. The average value of a constant is the constant. That should make a lot of sense here. So we have mathematically shown that the average value for our instantaneous power is simply the DC portion in a more mathematically rigorous way. Okay. This agrees 100% with our results from earlier that we were able to get literally just by looking at the graph and making a few simple observations here. Okay. So give me just a moment to take my asthma inhaler. Sorry about that. I wasn't sure if you guys could hear me wheezing, but I could, and it was driving me insane. So now what I want us to do is literally look at some examples. And so what I'm going to do is I am going to work on the in-class assignment with you guys. There are a couple of small nuance type things here that I want to make you aware of in the application of the equations that we have developed. So this should be in-class assignment number 22. All right. So in this first problem, we are told that a network, so this is a network, not a resistor, capacitor, or inductor, which means we need to be using our generic equation, has a frequency-dependent equivalent impedance given here, where the resistor value is 10 kiloohms and the capacitor value is 200 nanofarads. Okay. So the first thing that I want us to do is to find ZEQ. So that should just be literally plugging things in. So ZEQ is going to look like 10 kiloohms divided by the square root of 1 plus, so omega here is what?
$377.
Absolutely right. Times R, so 10 kiloohms squared times C, 200 nanofarads squared with an angle of the inverse tangent of 377 times 10 kiloohms times 200 nanofarads. All right. So I'm going to throw this into my calculator in two parts. I'm going to do the magnitude first. So 10 times 10 to the 3 divided by the square root of 1 plus 377 squared, 10 times 10 to the 3 squared, and then 200 times 10 to the minus 9 squared Calculator ran out of memory. Let's try this again. I think I had too many parentheses. All right, looks like I'm gonna have to do the denominator by itself first. Sorry about this. I get 7,984.643. My angle, I'm gonna have negative inverse tangent of 377 times 10 times 10 to the 3 times 200 times 10 to the minus 9. Negative 37.016 degrees ohms, and I'm going to store this in my calculator. As X. So we are going to wind up using our generic equation, right? I'm going to write it down here. P of T is equal to 1/2 VM IM cosine theta V minus theta I plus 1/2 VM IM cosine twice omega T plus theta V plus theta I. The reason why I just wrote that equation down is so we can kind of identify what information we have and what information that we are missing, okay? So we know what omega is because it was given to us here in the problem statement. And I very strongly believe that if we look at this whole piece right here, we can figure out what IM and theta I are. So let's take a crack at that, right? How would I represent I of T as a phasor? So this is a sine function, not a cosine function. So the first that I have to do is convert my sine function to a cosine function. How do I do that?
Isn't it cosine minus 90?
Exactly right. So I subtract 90 degrees. So that's going to be the same as 2 cosine 377t, and then 22 minus 90 degrees is going to be negative 68 degrees, if my mental math is working correctly. Milliamps. 90 minus 22 is 68. Yeah, that should work. So now that I have a cosine representation, how do I get my phasor? I simply keep my magnitude, keep my phase angle, and throw everything else away. So that's just going to be 2 angle negative 68 degrees milliamps, where this 2 milliamps is IM, and this negative 68 is theta I. So the only pieces of information that I'm missing to plug into my generic equation are now Vm and theta V. So how should I find that? Well, our phasor voltage V contains both of those pieces of information. And using good old Ohm's law, V is simply equal to I times Z. So if I multiply my impedance times 2 times 10 to the minus 3 to convert it into milliamps with an angle of negative 68 degrees, I wind up getting a voltage phasor of 15.969 with an angle of negative 105.016 degrees volts, where this part right here is Vm, and this part right here, excuse me, is theta V. So I'm now ready to just plug things into my equation, okay? So for my first bit here, I'm gonna have 1/2 times Vm, so that's gonna be 15.969 volts times Im, which is 2 milliamps, times the cosine of theta V, negative 105.016 degrees, minus theta I, negative 68 degrees. And in my second part, I'm going to have that same 1/2 Vm of 15.969, excuse me, volts, times 2 milliamps. Now I'm going to have cosine of twice omega, so twice 377 T plus theta V, negative 105.016 degrees, plus theta I, negative 68 degrees. Okay. So let's throw this first part in my calculator. So 1/2 times 15.969 times 2 times 10 to the minus 3. That gives me 15.969. So I'm going to hold on to that because that's this first bit right here. Multiply that by cosine of negative 105.016 minus negative 68. Missed a negative sign there. Negative 105.016 minus negative 68. There we go. 0.01275 1 plus 0.015969 times the cosine of 2 times 377, 754. And then negative 105.016 minus 68. Negative 173.016 degrees watts. And to get rid of some of these things, we can call this 12.751 plus 15.969 cosine 754t minus 173.016 degrees milliwatts, which is exactly the answer that we were expecting. Okay. So the reason why I worked out this specific problem is I wanted to illustrate, this is the first time we've done this in quite some time in this class, but the relationships that we're given are straight plug and chug, okay? So what I mean by that is we should still be doing literally all of our analysis and relationships in the frequency domain, and then just taking the bits and pieces that we need and plugging them into our equation, okay? So the instantaneous power equation is literally just that. It's a time domain relationship where we're plugging in our frequency domain things as we need them. All of our circuit analysis should still be occurring in the frequency domain. Right? So let's look at problem 2. In problem 2, we have 3 circuit elements are connected together. A current source, a resistor, and an inductor. So I'm going to draw this out for us. So here's our current source connected in parallel to our resistor, which has a value of 1 kilo ohm, connected in parallel to our inductor, which has a value of 15 millihenry, like so. What will this circuit look like in the frequency domain? So what is the phasor representation of this current going to be? What's the magnitude? Sorry. go for it.
Magnitude is 100. I can't answer that.
Okay. So the magnitude is 100 milliamps. I'm going to be a little lazy and call this 0.1 amps.
Yeah.
What's the phase angle?
10 to the
0.
5.
So the phase angle is 0, right? So 2 times 10 to the 5 is omega times t plus some phase angle theta I, right? Well, that phase angle in this case is 0 degrees because there's not one given.
Oh, okay.
So the bit multiplied by, that's being multiplied by t is always omega. All right. Now we have our resistance. Well, what's the impedance of a resistor?
It would be 1 angle 0.
Sure. I'm just going to leave it as 1 kilo ohm.
Okay, yeah.
The exact same thing, right? Purely real. What's the impedance of my inductor? So the equation for the impedance of an inductor is J omega times L. So I'm going to have 2 times 10 to the 5 multiplied by 15 times 10 to the minus 3 gives me 3,000. So this is going to look like J 3 kiloohms or 3,000 angle positive 90 if you prefer the polar form representation of that impedance. So we've converted our circuit from the time domain into the frequency domain. Okay. We are now trying to find the instantaneous power absorbed by each of these elements at a specific period in time. Okay. So I want to point something out here. We're looking for power absorbed. So I believe that if we can find this phasor voltage V, that should be all of the additional information that we need. Okay, so let me explain my reasoning for that. If we look back at our notes, here, I have an equation for the instantaneous power absorbed by a resistor purely in terms of the voltage, right? Because it's based on the magnitude of the voltage and the phase angle of the voltage. Here, I have an equation giving me the instantaneous power absorbed by an inductor, also only in terms of the voltage. For my current source, I'm going to have to use this relationship, but I already know the current through my current source, so the only other piece of information I need is the voltage. So if we can find the voltage, we have everything that we need. So how do I find the voltage phasor V for this system?
Would we apply those two equations to their respective impedances and then perform a parallel?
So this is a circuit analysis problem. We're not worried about applying the equation yet. We're trying to collect all of the data that gets put into the equation. Okay.
Would you
how
use
do I-
current division?
We could. There's nothing particularly wrong with current division, but current division is just going to give us the current flowing here or flowing here. And that's not what we're looking for. We're looking for the voltage. Now we could use current division and then multiply by those impedances to get the voltage, but we could do that in one step simply by applying Ohm's law, right? So what I mean by that is 0.1 angle 0 degrees amps multiplied by these two impedances in parallel is going to give me the voltage in a single step. We don't have to make it harder than it needs to be. If Ohm's law will get the job done, let's just use Ohm's law. So to me, this is going to look like 0.1 angle 0 degrees amps. And then my parallel impedances. So I'm going to have 1 kiloohm times J 3 kiloohms divided by 1 kiloohm plus J 3 kiloohms. We throw that in my calculator. I get 94.868 angle 18.435 degrees. Volts. Which means this bit right here, excuse me, is VM. And this bit right here is theta V. So now we have all of the information necessary to apply our equations. So which element do you want to solve for the instantaneous power for first? The current source, the resistor, or the inductor?
I'm just picking from left to right. I would say the current source.
Okay,
Unless there's a smarter way to approach it.
nope, that's perfectly reasonable. We're gonna repeat effectively a similar process for all of them. The current source is definitely the trickiest one technically, and I'll explain why here in just a moment, okay? So for our current source, we're gonna use our generic equation. So that means we're gonna have 1/2 VM IM cosine theta V minus theta I plus 1/2 VM IM cosine twice omega t plus theta V plus theta I. So let's plug some stuff in here. 1/2 VM is 94.868 volts. IM is 0.1 amps. Cosine theta V 18.435 degrees. Here's a tricky bit, and you're gonna think I'm being weird, but I'm not. What's the angle for theta I that we should use?
0.
I disagree. The reason that I disagree is because we're calculating the power absorbed by each element, right? So effectively, we either need to change the polarity of our voltage or change the direction of our current in order to make this work out, right? Because as we have it right now, the current is flowing into the negative polarity terminal, which means if we use 0 degrees, we're calculating the power supplied. So we can take care of this simply by changing the angle of our current by exactly 180 degrees. Because that is the exact same thing as multiplying by a factor of -1. So that passive sign convention stuff that we talked about on literally the second day of class, and I told you it was going to annoy us the entire time through this class, is still popping up, okay? So this 180 degrees right here is because we're looking for absorbed power. And we chose to find the voltage with positive polarity on top, like so. All right, so now down here, we're gonna have 1/2 VM, so that's 94.868 volts, 0.1 amps, cosine 2 times 2 times 10 to the 5. I'm going to be explicit here and put this as radians per second because we're multiplying by a specific value in time, 10 microseconds, right? So 10 microseconds is 10 times 10 to the -6 seconds. And then out over here, we're going to have theta V 18.435 degrees plus theta I 180 degrees, and close this off. I've left the space here because over here we have an angle expressed in degrees, expressed in radians. So I'm going to need to convert one of these. So if I convert this one, it's going to be from radians to degrees. If I convert this one, it's going to be from degrees to radians. because my calculator is already in degree mode and I'm very lazy, I'm going to convert this thing right here. And so that conversion factor is simply 180 degrees over pi. So now I'm going to put this into my calculator. So 1/2 times 94.868 times 0.1 gives me 4.743. I'm going to keep that. So I'm going to just store this as X in my calculator. So X times the cosine of 18.435 minus 180 looks like negative 4.4999 or negative 4.5. Get something so wildly off. Let me double check this real quick. 1/2 94.868 0.1. Well, that is X. X times cosine 18.435 minus 180. Oh. Sorry. I was confusing myself because I saw this answer of negative 2.694 watts, not thinking about the fact that we have not taken into account this big thing right here. So this negative 4.5 watts comes from this first calculation. For our second calculation, we're going to have what I have stored as X times the cosine of 2 times 10 to the 5 times 10 times 10 to the minus 6 times 180 over pi plus 18.435 plus 180 . 1.806 watts. Add those together. Negative 2.6946938 watts, which agrees with what the solution should be. Okay. So one of the biggest things that we need to watch out for if we are trying to take our instantaneous power equation and use it to evaluate the instantaneous power at a specific point in time is the fact that this angle right here is going to give us something in radians, and this combination of angles here is going to give us something in degrees. So if we do not make sure to convert one to the other, so radians to degrees or degrees to radians, our calculator is going to give us an answer. It's just going to be very, very wrong. Okay, so that is another thing that I wanted to point out to you guys. All right, so this the power absorbed by the current source is by far the hardest one to deal with because it's the first time that we're seeing we need to include this conversion factor. And then also we had to shift the phase angle of our current by 180 degrees to take into account that we are finding the absorbed power, not the supplied power. For our resistor, things should be a little bit more straightforward. So we're going to have 1/2 VM squared divided by R times 1 plus cosine twice omega t plus twice theta V. So that's going to be 1/2 times 94.868 volts squared divided by 1 kiloohm times 1 plus cosine 2 times 2 times 10 to the 5 times 10 times 10 to the minus 6 times 180 over pi plus twice 18.435 degrees. So again, I'm going to split this thing up into two parts. So 1/2 times 94.868 quantity squared divided by 1,000 is 4.5. Again, I'm gonna have 1 plus cosine 2 times 10 to the 5, 10 times 10 to the minus 6, 180 over pi plus 2 times 18.435. I get 4.190 watts. Exactly as what was expected. Lastly, we have the instantaneous power absorbed by our inductor. 1/2 VM squared over omega L times the cosine of twice omega t plus twice theta V minus 90 degrees. That's going to look like 1/2 times 94.868 volts squared divided by omega L was 3,000 ohms times the cosine of 2 times 10 to the 5, 10 times 10 to the minus 6, 180 over pi plus twice 18.435 minus 90 degrees. Cosine 2 times 10 to the 5, 10 times 10 to the minus 6, 180 over pi plus 2 times 18.435 minus 90. I get negative 1.496 watts. So with rounding error, that makes sense. And honestly, there was a technically shorter way that we could have done this. So if this is the power absorbed by the source and this was the power absorbed by the resistor, adding these the source plus the resistor plus the inductor all have to add together to make 0. So we could have just used intelligence theorem from the second day of class as well. But I wanted to show you how to apply the equations. All right, so once again, just rehashing things here, all of the circuit analysis that we carried out to solve this problem was carried out in the frequency domain. We then took information from our frequency domain representations or our phasors and plug that stuff into our equations. That's all we're ever going to do to apply these equations. For our last problem here, we are asked to determine the average power absorbed by each element in this network. We are already given the network in the frequency domain, so we don't really need to do a whole heck of a lot of, or literally any transformation here, converting from the time domain into the frequency domain. We simply need to do our frequency domain circuit analysis. Okay. So let me look at this guy really quickly here. I am going to choose. So let me label stuff that we're going to need effectively. So in order for me to figure out the instantaneous power absorbed by my current source, I would want this phasor voltage, positive polarity on bottom. Okay. To find which happens to be the voltage drop across the 4 ohm resistor as well, and I can use that to find the instantaneous power absorbed by the 4 ohm resistor. Another thing that I could use would be this current. Because that's going to be necessary to calculate the average power absorbed by the voltage source. And I could also use that to calculate the average power absorbed by the capacitor, but we know that the capacitor's average power is 0, so we don't actually need to do any work for that. So this begs the question then, what's the best way to solve for these two quantities? How I am going to approach this problem is by putting ground down here at the bottom and solving for this nodal voltage Vx. And the reason I'm doing that is because I can see by inspection that VCS is just negative Vx, and IVS is going to be Vx minus 4 angle 30 degrees volts divided by minus J2 ohms. So if I know Vx in 2 steps, I will be able to get all of the other information that I need. So to solve for Vx, I'm going to write KCL at this node. So adding these 3 together, I'm going to have negative 12 angle 0 degrees amps plus Vx over 4 ohms plus Vx minus 4 angle 30 degrees volts divided by minus J2 ohms is equal to 0, which means Vx multiplied by 1 over 4 ohms plus 1 over minus J2 ohms will be equal to 12 angle 0 degrees amps plus 4 angle 30 degrees volts divided by minus J2 ohms. So that's going to give me Vx is equal to, and I'm just going to throw this stuff into my calculator really quickly. So 12 angle 0 plus 4 angle 30 divided by minus 2i gives me that number. 1/4 plus 1/-2i. It's going to give me this number, which I'm going to call y. X divided by y. 19.920 with an angle of -54.487 degrees. Volts. So PCS. Let's see here. We're going to have 1/2 times the magnitude of the voltage, 19.920 volts. The magnitude of the current is 12 amps times the cosine of theta V. So that's going to be -54.487 degrees plus 180 minus theta I, which was 0 degrees. I get -69.428 watts. Exactly what we're expecting. For the resistor, we're going to have 1/2 VM squared over R. So that's going to be 1/2 times 19.920 volts squared divided by 4 ohms. So that's going to look like 1/8 times 19.920 squared. Positive 49.601 watts. The capacitor we were able to do by inspection. Lastly, we have our voltage source. So ICS was Vx minus 4 angle 30 degrees volts divided by minus J2 ohms. X minus 4 angle 30 divided by -2i gives me 9.969 angle 23.994 amps. And so, sorry, it should be VS. Power absorbed by our voltage source is going to be 1/2 times 4 volts times 9.969 amps times the cosine of 30 degrees minus 23.994 degrees. I get to be 19.828 watts. Exactly what we have here. All right. So I've worked all 3 of the in-class assignment problems to illustrate to you guys how to put into practice the equations that we have developed during the lecture portion. I've also identified some areas where students tend to stumble. Is there anything else that I can help you guys with today?
So it really looks like for these, we just plug them in to the equations, and then for problem, especially problem 2, we just need to be aware that we need to convert the trigonometric function into that polar representation.
So, any time that you're given a circuit that is sinusoidally excited, you should be working it in the frequency domain. So it's not just for problem 2, literally anytime. That's all we've been doing for the last several class meetings. If we don't convert it into the frequency domain, we have to use all the terrifying trig and stuff that I worked with like 2 weeks ago at this point, where I spent 45 minutes working an even simpler problem than that one. So anytime you're given a source that is sinusoidally excited, convert it to the frequency domain. So use phasors and impedances.
Okay.
So just for the sake of argument here, let's look at the web work just really quickly. I will point some things out. So this should be homework set number 21. Might be 22 actually.
Yeah,
22.
21 has op amps,
Yeah.
or at least problem 1 did.
Yeah, so 21 is just generic steady state sinusoidal circuit analysis, so analysis stuff. So effectively, if it's not given to you in the frequency domain, convert it into the frequency domain and then do your analysis. All right, so this particular problem right here is more sinusoidal steady state stuff. I think we talked about it very briefly at the end of class on Thursday. This is literally nothing more than the analysis that we had been doing before today. This particular problem is exactly in class assignment problem 2, except that the numbers are different. For this particular problem, you're finding the average power delivered to each of these impedances if Vs is equal to 5.8 angle 171 degrees. Extremely similar to ICA problem number 3, except that now everything is a combination impedance, which means you won't be able to use our shorter equations, right? So in this example, right, we have a resistor and a capacitor, which allowed us to use the equation for resistors, and the capacitor we were able to do by inspection. For the web work assignment, we have an impedance that is a complex number, meaning that this one, for instance, contains both a real part and a negative imaginary part. This one has a real part and a positive imaginary part, etc. So we're going to have to use the generic relationship, which means you're going to need to know the voltage drop across and the current flowing through all of those impedances. Luckily for you guys, this should be fairly straightforward. For instance, the voltage drop across the 6 minus J8 ohm impedance is Vs because they're in parallel. The current flowing through the 6 minus J8 ohm impedance is just Vs divided by 6 minus J8 ohms because of Ohm's law. The current flowing through this 4 plus J2 ohm impedance is the same as the current flowing through this 8 plus J7 ohm impedance because they're in series. And we could find that current simply by dividing Vs by that series impedance. And then we could use Ohm's law to find the voltage drop across each of those. Once we know the voltages and currents, we can use the equation that we developed at the beginning of class. For problem 4, we're trying to find the average power delivered to a resistor by each of these waveforms here, right? So we're given the current. I didn't explicitly give you an equation for this, but this is going back to, we go to the notes here. Really this bit right here, right? So let's say just for the sake of argument, since we're dealing with a resistor, the instantaneous power absorbed by a resistor is just going to be the current squared times the resistor value, which means the average power is going to be 1 over the period times the integral over 1 period of I squared times R dt. Since the R is a constant, we can write this as R divided by T times the integral of I squared. So the absolute hardest part of this particular problem is going to be figuring out how to express these current waveforms as a function of time. This one is obviously a piecewise function. This one is obviously a piecewise function. This one, it specifically tells you each segment is 1/4 of a sine wave having an amplitude of 8.5 milliamps. So it's going to be very similar to homework 19 problem 3, I believe, where you had to reconstruct the mathematical form of a sine wave when you were only given the information for 1/4 of it. So it's nothing that you haven't been asked to do previously. It's just putting it in a new application. All right. Anything else?
Would it be asking too much if we could get the upload of this video today?
I will do what I can do. The sooner I stop talking, the sooner Zoom will start processing it.
Fair. I don't have any questions right now.
Good to go.
All righty. I'm sorry, what was that, Dave?
Good to go.
All righty, well, we'll see you guys tomorrow afternoon, and I will endeavor to get this up as soon as possible.
Okay, I appreciate that.
No problem.
All right, bye.